How's it going, everyone? Thank you so much for watching this video at your own leisure. I really highly recommend you check this out before you even begin the practice quiz problems, because this is going to help with regards to circular motion content. So before we get into that though, I want to thank you guys so much, you gals and guys, for sound like for the effort and the perseverance you guys put each week, especially today when we had our exam. So I'm recording this on Tuesday. It honestly makes me feel really grateful for everything you guys have done and how much you guys push forth, because it's not like this is a regular semester where like things are spaced out a little bit more slowly. This is like 2 chapters per week, and this is something you guys chose to endeavor through, and I can see it in the maturity that you guys put forth in your education. I always notice the questions, the comments you guys always make, and that speaks volumes of your character, because it shows me that you're trying to understand and learn and excel for various purposes, because this is kind of like a stepping stone into something that you're trying to do. And even though it doesn't fully like at all relates to your goal, there's this endeavor you have to get through. And so I really appreciate everything you guys have done. The exams can always be brutal, and honestly, like, thank you for pushing through. Honestly, I really appreciate it. But with that being said, um, let's see. Any announcements? So we're gonna jump into the topic now. Break it down into the basics. As I go through this, now this is new content. Start your equation sheet now if you want. Any equations I use, write these down on like a separate piece of paper or on your tablet, whatever you have to write things down, and save it. And as we go through each chapter and I focus on specific equations, write these things down and try to remember how you can apply them to different scenarios that we will talk about. So it's circular motion today. And because I pretty much canceled the lecture part today, because you guys deserved it after all the effort, always having to wake up early at 10 a.m. and being on time. And you guys are pretty good about it, which I really appreciate. I decided it's best to let you guys go after the exam, and then you guys can watch this video whenever you guys have time. You guys can rewind it, go back to it, email me if you guys have questions, or leave comments down below if it's something that maybe benefits some of your other classmates. These videos that I make, well, there's only like 2, the first one and this one, are always unlisted, so no one can see them besides you guys. So in case you guys wanted to know. So let's switch over to the shared screen. I was having issues with the whiteboard earlier. Let's see if it, because I got a new tablet thing. And so, yeah, I think I still have the issues, whatever. Okay, circular motion. What's so special about it, and how does this connect with everything we've talked about in the past? So let's start off with the idea of speed and velocity. So we know the two difference, right? Speed is only the magnitude. We don't include the direction and speed. But for velocity, you focus on both velocity, on direction and magnitude. And we talked about that situation with the circular motion, going in a circle, and how if you have constant speed, you can still have an acceleration because you're changing your direction. And so that's why you have an acceleration. But the thing I never indicated is where, like physically, if we draw the acceleration, where is it? Like, you just know, okay, there's an acceleration, but what is the acceleration? So let's get to it. So first, blue arrow is going to indicate velocity, and green arrow is going to indicate acceleration. Just if you guys are wondering. By the way, this is super laggy, so I hope it doesn't get screwed up. For some reason, when I'm recording, it like lags for some random reason. I need to fix that. But anyways, let's go to the arrows. If you're here, your arrow is pointing in this direction. If you're here, the arrow is pointing there. So you guys already, I hope, are a little familiar with this idea. and here the arrow would point here. So we can see as you go in a circle, the arrow is pointing in a different direction. It's pointing up at one point, it's pointing to the side, then downwards, and then the other direction. So full circle. And the idea is that there is an acceleration that is pulling the arrow in that circle. And the way it's pulling the direction to turn is inwards, boom, 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 in that circle. And so if we have the center point of the circle there, the arrow points downwards, inwards, I mean, radially inward. Boop, boop, boop. And if that doesn't make sense, let's think about it this way. If I have this pen, assume this is a vector. In order for it to turn, I have to pull it, right? I pull it, and then as it's moving, it starts to change direction, and then it goes in the circular pattern. The only reason that's happening is because I'm pulling it inwards. I'm not pushing it outwards, I'm pulling it in. That's where the green arrow comes into play. Here too, the arrow pulls it down, and that's what causes the arrow to start turning, boop, like that. And so that's why you have this acceleration that pulls inwards everywhere. So the idea I want you guys to take away is that the acceleration in the circle, let's redraw the circle next to here, always points radially inwards. That's just the term used. Radially means it points in that same direction in whatever position of the circle. So if this is the center point, is pointing radially inwards. If you're traveling in a circle, the acceleration is pointing inwards. And so you'll notice the acceleration, the magnitude should be the same, but of course the acceleration points in different directions depending where you're at on the circle. Another example of this situation is on a roller coaster. If you go like, sorry, this is gonna come out really bad. Oh, this is terrible. Like the lag is just unbearable. Let me do it a different way. Let's insert this and this, just to avoid the lag. Let's assume this is a coaster that connects. So if you are a roller coaster, this is the cart, and it starts moving this way, and then it goes up here and comes back down and then comes through here. You experience that same acceleration inwards as the coaster is here, as it's moving here, as it's coming back down here. There is this acceleration pointing inwards to that center point in the circle. Okay. The reason I'm bringing all of this up, sorry, I elongated this idea, is there's a specific term that is attached to this type of acceleration. This acceleration that is only produced when you go in a circle is something we call a centripetal force. And so I'm gonna write it right here, centripetal. I can't spell it, but spell check will help me out with that. Centripetal acceleration. Okay. So this type of acceleration is called centripetal acceleration. This idea of centripetal, anything, because we're going to talk about this a little bit more, should just trigger an idea of going in a circle. And so centripetal acceleration as A, you may be wondering, how can we find what that acceleration is when you're going in a circle? Because you're not changing your velocity, you're only changing your direction. So how can we physically, because if you have a change in magnitude, you can just use this equation, change in velocity over the change in time. You figure out the difference in your velocity over however long, how much time passed through that. But how do you do it for something that doesn't change the speed, the actual, because if it doesn't change the speed, this top part would be 0 over time, whatever the time frame was, and that would be 0. So it wouldn't make sense, right? So here is how it works. The way to define centripetal acceleration, I'm going to put a C for centripetal, is as follows. The speed squared over the radius, R. I'm going to put capital R just to avoid any confusion, because sometimes I write my R's like B's, it looks like B's. So like this, write this equation down, you guys. It's such an important one. Oh my goodness, this lag sucks. Okay, like that. So you have V squared over R. So now if you have a problem where I'm asking you, hey, can you calculate the centripetal acceleration? The two pieces of information you need to know are 1, the speed, 2, the radius of the circular path. When you're thinking of a circle, there's a few terms that, oh, that's not going to help either. There's a few terms that we want to take. Sorry for all these technical issues. I got a new graphics tablet, and I thought it'd be better. But anyways, so when you're looking at a circle, there's a few, and I can't think of the word, like different ways you can describe certain parts of the circle. The first one is the length from here to there, wherever it ends up. Here, I'm not gonna do that. Let's put this like that. That's so much easier. That's called the diameter, right? The diameter. So I'm gonna write a D for it. But now if you cut that diameter in half, that's the radius. So in half from here to there, like that. And so 1 is an R. I'm gonna use capital R for both of them, just to keep consistency. So that means if you're trying to find the radius from the diameter, 2R is equal to the diameter. Okay, but anyways, more than likely, information will be given in terms of radius. And of course, radius, diameter, they're all distances. So standard unit for them are meters. And so the radius goes from one end of the circle all the way to the center of the circle, as you can see by this little dash right here. And that's the radius. So that's what that R represents. So if you're given the radius of the circle, of the path, circular path, or the object that's circular, and you know the velocity, the radial velocity, then you can plug it in to find your centripetal acceleration. So that's the first key thing. And this is going to build up now, because now that we have this tool, let's look at Newton's first law. Force is equal to mass times acceleration. So you might see where I'm going with this. If I have this equation and I want to replace the acceleration with the centripetal acceleration, this is what's going to happen. So mass, and then instead of the regular acceleration, we're going to plug in the centripetal acceleration, which is V squared over R. So you may be wondering, what does this do? By doing this, we've introduced a slight variation of a new force. We call it a fictitious force because it only occurs when you're going in that circle. And so this is what we call centripetal force. So I'm going to put a little C right there. And this is another equation you want to have down. This is not going to look good. Okay, there we go. You only want to use this equation when the situation encounters a circular path. So hopefully you guys, I've engraved that idea. Use this for circular path. Okay, so now you may be wondering, how the heck do I apply this to anything. So if I were to ask, so let's give ourselves some examples here, similar to what you guys have in the practice quiz, but not the exact same problems. Okay, say you're the International Space Station. So that the space station is this space laboratory that's orbiting around the Earth. And so if I'm gonna use circles from here because my pen is so glitchy. So here, that circle is Earth, and the space station in blue is gonna be this little dot right here, right there. And so what I'm gonna do is I'm gonna insert another circle. And this circle represents the path of the orbit of the, there we go. So the blue, think of that as the path that the satellite, that the International Space Station takes to go around the Earth. So if it travels in that direction, it's moving here, it's moving there, it's moving there, it's moving here. And the reason why I bring this problem up is because there is one thing that we need to clarify of how we treat values that were given. If I ask, let me write down the problem right here. The International Space Station travels, and I'm making these numbers up, by the way, travels at 45 meters per second. So the speed is 45 meters per second, but it's changing direction. So you should contextualize that when you see circular stuff. You're like, okay, cool. It travels 45 meters per second all around at an altitude of 250 meters. So I'm making these numbers up. It's actually like kilometers, but I digress. What is the centripetal force? I thought I was going to spell it right. Centripetal. Oh, it's a T. Oops. What is the centripetal force on the space station? So that's the problem. Using this idea of centripetal force, we want to figure out what the force is. Because we know if acceleration pulls inwards, the force also pulls inwards, because force is just mass times the acceleration. So essentially, you're just multiplying mass to turn that centripetal acceleration into a force. So we want to know what the magnitude of that force is. Okay. So there's a few things we need to cover. Let's write the equation down. Centripetal is equal to mass v squared over r. When you read this problem and you see altitude, 250 meters, that is the distance from the ground on Earth up into space. So that means from here to here, that is the altitude, 250. We're assuming, because that's not true, but for the sake of this example. So then you may be wondering, okay, do I just plug in 250 meters here? That would be incorrect. And I wanted to clarify this because this is going to happen a lot. This happens a lot where people just plug in 250 and that's not correct. If you want to find the centripetal force, so we already know what the speed is. It's 45. We'll plug that in here. You would be given that. I forgot to give you one other piece of information. The mass of the station is 50 kilograms. We're going with something light. So you would plug everything in, but you wouldn't plug in just 250. And here is why. As I mentioned, the radius is the distance from the object to the center of that circular motion. So if the blue circle is how it's supposed to be, the altitude doesn't justify the radius. That's only a little part. The total radius would be at the center here, all the way up. So it would be 250 plus this distance. Okay. When it comes to Earth, you can just look that information up. Just go on Google and put what's the radius of the Earth, and that would be your actual distance, and you would have to include that in there. So the total radius would be equal to the 250 meter altitude plus, so you just add, plus the radius. I'm going to put an R, and I'm going to put E for Earth, whatever that is. Whatever you get for that addition, that's what you plug into this equation, and then you can solve for the centripetal force. For the sake of simplicity, we're going to make up a number for the radius of Earth, but again, for homework, you can just look it up on Google. For exams, you will be provided with this information if I ask you for something like that. Let's say the radius of Earth is equal to 500 meters. By the way, if you get different units, you're going to need to convert to meters. So if you get kilometers, you got to convert. So let's plug everything in and see how it turns out. The mass is 50 kilograms. So I'm just going to avoid units just to simplify everything. V is 45 squared. Don't forget to square that. And you divide all of that by the radius, which is the addition of these two. 250 plus 500, that is 750 meters. And so plug that into your calculator. Whatever you end up getting, that's going to be your centripetal force. Any questions? Just kidding. You guys are just watching this. I'm just so used to asking questions. But yes, that's how you solve centripetal force. So this is one concept that you want to take away from this. But we're not done. We're going to build more to this. I'm just right now thinking of how I want to segue into this, because there's a few ways I can do this. There is another equation that you're going to use. So going back to Newton's first law, mass times the acceleration, that's normally used on Earth. As you saw with the centripetal force equation, we can use that in space. You don't have to be on Earth to use this equation. You can, but you can be anywhere. Just knowing the distance from where you're at in space all the way to the center of the Earth, if you're orbiting around the Earth, you can figure out some information like the centripetal force. This Newton's law, unless you tweak it like this, you only use this when you're on Earth, like solid ground, because there's no place. You just know your acceleration is g, 9.8, and then you just figure out your mass. But you cannot just use this plain equation like this when you're out in space, because the further you're at from Earth, the lesser the gravitational pull you feel. So g wouldn't be 9.8 the further out you go. So that's where you have to use centripetal acceleration to give you that information. But there is another equation too. I'm not going to derive it. I was thinking about doing, I'm like, no, that's just a waste. I want to just write it down for you guys. This new equation is as follows. There's a new constant. It's called big G. You can just call it capital G times big M times little m. Let me make sure. Divided by radius, but this one's squared. So slightly different than the centripetal force. This equation you can use anywhere. You don't have to be going in a circular orbit. You just need to be in space and compare it to whatever scenario you're looking at. Make sure to include this equation too into your equation sheet. So this equation is actually really, really powerful, because what this is saying is, in order to find the force, all you need to know are the following things. G is a constant, so that's a given piece of information that you can just Google right now and it gives you the value. For the sake of simplicity, I'm not going to write it down, but definitely look into it. The big M is the mass of the bigger object. Small m is the mass of the smaller object. For the example of the satellite, the big M represents the mass of the Earth. Little m represents the mass of the satellite. And then the radius squared is the 250 plus the radius of Earth. But then you have to remember to square it. Add those two terms, get the total radius, not just the altitude, but the radius, and square it. That's really key, because these mistakes happen a lot where people just get the altitude and square it and that's it. But that would be wrong. Okay, so again, you can look at the other example and you can get the force too here for that. Okay, now I'm gonna combine these two equations somehow, because the force, the standard force, the universal force of gravity, we can call this that equation, is equal to centripetal force. So if you have both, you have these two equations in your arsenal of tools, they're both equal to each other. So here's how you might apply this equation. So here's how it goes. I am going to draw a little circle, and here I am in space. And I'm going in a circular motion. So I'm orbiting around, doesn't matter which direction, but I'm just going to choose to go clockwise. If my altitude is 100 meters, and just say this is some random planet, let's say it's like an asteroid. The radius of the asteroid is, actually, let me use a different color just to differentiate it. The radius of the asteroid is 10 meters. Then we have that information set, right? Actually, that's not what I wanted to do. Okay, no, that works. We're going to do it this way. So now my question is, okay, here's another piece of information we need. My mass is 50 kilograms. The mass of this little asteroid, big M, let's just say it is 1,000 kilograms. What my question is what speed, what speed do I need to have in order to keep a perfect circle around this asteroid? If I ask you that, then you know, okay, I need to use centripetal force equation because I'm going in a circle. But the thing is, with the information, so let's write this down. Centripetal force is just mass. And this one, let me one piece of information I haven't gone over, the mass. You may be wondering, wait, is the mass of the bigger object or the smaller object? It's a little m, so it represents the mass of the little object. So in that case, it would be me, the person going around orbiting the asteroid. So we have the information for this, and we have the information for this. It's 100 meters plus 10 meters. That's the total radius of where I'm at with respect to that asteroid. And we're trying to solve for the speed. But we can't do that. We don't actually know the centripetal force. Ugh. And so that leads us into needing another equation to replace this value that we don't know. That's where the universal force of gravity comes in, the equation for that one, this equation. What we do now is we're going to replace this, since F is equal to F centripetal, we're going to replace this in here with this equation. So what that means is we have G times the big mass times little mass divided by radius squared. That is equal to mass times V squared over R, big R. Okay. So this is going to get us our answer because we're going to have everything else. But before we do that, before you plug in values, always try to simplify these equations because it just makes our lives so much easier. What is one thing in common you see on both sides of the equation? What you see is that little m is in both of these. So if you divide little m, it cancels them out. So boop and boop. So now we don't have that. Another thing is you have one R and then two R's here. So so let's first figure out, we're trying to find the velocity. So I need to move this one R to the other side. So I'm just going to multiply it because I want to isolate V. So that cancels that out. And what that does when you have this situation, there's two R's. That's what that represents. The square just means it's R times R. So one R cancels one R here. And what you have left over, if we just kind of write down what we have left over, is this G, it's a constant. Constant means it's a value that is given, that is known. It doesn't change, doesn't matter the situation. We have the mass. The mass changes depending on what object you're orbiting. So that's why it's a variable. Divided by R, and that's equal to V squared. Last thing to do, we need to reduce this, so we square root it. And what we get is V is equal to all of that over R. There we go. See, we've simplified before we even plugged in everything. This makes us realize we didn't need all of that information. We didn't actually need to know my mass. We only needed to know the mass of the planet or the asteroid in this case, G constant, and the radius. So when you look at radius, you have to remember you're adding these two distances, the radius of the asteroid plus the altitude at which I'm at with respect to the asteroid. So we would plug in the value for G. I'll mention it right here. M is 1,000. Sorry for the slow poke writing. This tablet's so slow only when it's recording for some reason. The radius is 100 plus 10 because you're trying to get the radius of the circle that you're actually traveling around, not of the asteroid, but of the actual orbit you're making, which the center is right here. So from here to up here, that total distance is the 100 meters plus a 10. So that's 110. 110 meters. And then you square all of that and you're going to get your velocity in standard units, meters per second. And that's how you get that answer, by combining these two equations, just looking at the concepts of rotation and just memorizing this other equation for the standard, the universal force of gravity equation. Where is it? This one right here. You can solve a lot of information and make sure to combine them. That's key. Okay, I've already taken some time out, but we're almost done. Next up, I want to get into, because now we're moving into rotational stuff. And so when we get into rotational stuff, I'm going to draw another circle. But now we're going to go back to Earth. So here's a circle. We're going to assume that circle is a tire. And I need an arrow to indicate the ground. Okay, so here we have it. This tire belongs to a car. I'm not gonna draw the whole thing, but you get the gist. It's spinning, it's moving in this fashion. And so when we talked about kinematics at the beginning of the semester, and I think it's like for a good chunk of time at the beginning, we only looked at things moving in straight lines, or the initial conditions of how the velocity goes in the x direction or in the y direction. We can get that velocity of the tire, like as the tire rotates. If I tell you that the speed of the tire is 5 meters per second, that's how fast the tire is moving across the street. But if I want to know how fast it's rotating, it's a slightly different thing, because that's not its velocity linearly, it's its velocity in the circular pattern. Like, how fast can you rotate something? And there's a term for that. We call that angular velocity. We use this weird Greek term called omega. And omega, like this kind of interesting looking W, represents a rotating velocity. And how you relate angular velocity to this linear velocity, like straight velocity. So actually, let me do this, because the arrow that represents the circular path, I'm going to color code it omega. There we go. And the linear path that the wheel is taking is the red, representing linear velocity. So the way you relate angular velocity is as follows. It's angular velocity is equal to linear velocity divided by the radius. So you guys are getting this idea now of how radiuses are really important when you're talking about circular things. And so that's how you can get this idea that we call angular velocity. And all you need is your linear velocity right here and the radius. If I tell you that the radius of this wheel is, let's go with 0.5 meters, then all you have to do is plug all your information in here. And so velocity is 5 meters per second divided by the radius is 0.5 meters. And so if we plug this into our calculator, I'm just trying to do the mental math, it would be 10. And the reason why I'm trying to write this whole thing out is because the units are going to be really useful, like to understand what kind of units we get with this new angular concept. So there's meters on top, meters on the bottom, they cancel out. And then what you have left over is in the denominator and the S. And so you have seconds. And then you may be wondering, what do we put on top? It's 10 blank per second. When you're talking about standard units and you're talking about rotation, this is where this new concept of radians comes into play. Whenever there's no unit here, this is something called radians. So when you look at the units for angular velocity, this is what they are, radians per second. And you may be wondering, what the heck are radians? And why isn't it just in degrees, right? Because radians is a unit of angle, just like degrees. But there's a little difference between them in how they get the information. So that's where it comes from. The radians is like always there, but it's hidden. That's like the idea that I learned when I was taking this. And so that's where it comes from. It's just there. It's just the angle it's taking per second. So it rotates that much radians every second. Okay, you may be wondering now, what the heck is radians? So let's kind of talk about that. So I'm gonna draw another circle, 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 circles. We know in degrees what this whole circle is. If we start here and we go all around and come back to this point, we've traveled 360 degrees, like that. Now you may be wondering, how much is this in radians? And so even if you don't have a grasp of radians, because I feel like it's something we don't really use, I want you guys to understand how you can compare the two. Going around in a circle once is 360 degrees. In radians, it's 2 pi radians. This pi is a number. It's actually more than this, but I'm only going to write the first 3 digits, 3.14. Hopefully you guys have heard of it. If not, that's what pi is equal to, approximately 3.14. I don't want to get into the extensive understanding of where pi comes from. I could, if you want, honestly, I'd be super happy to talk about it. It's related to the circumference and the diameter, but there's this ratio. But anyways, if you do, I can more than happily talk about this. Trust me, I was just getting happy mentioning the few things I did right now. But radians is in these weird terms. 360 degrees is equal to 2 pi radians. So now, if we don't travel the whole circle, but we only travel from here to here, that distance, that going from here to here is only 180 degrees. In radians, if 180 is half of 360, then in radians, it has to be half of 2 pi. So half of 2 pi is just pi radians. Okay, there you go. So before we get into talking more about angular velocity, there's a question I think on this where you might have to convert between degrees and radians. And so here is the conversion. If I give you 37 degrees and I'm asking you, hey, can you convert this to radians? This is how you do it. We already have 2 ways of looking at comparing radians to degrees. We know 100 centimeters is equal to 1 meter. So if we're converting 2 meters to centimeters, we just multiply this ratio onto here, right? 2 meters times the ratio. We'd put 1 meter down here and 100 centimeters up here, because that's how you cancel that. With the same logic, we're going to do the same with degrees. Let's look at this one right here. If 180 degrees is equal to pi radians, then we already have the ratio. We just have to multiply it by the ratio, right? So we put 180 down here because the little degree sign is at the bottom and this one's here. So that's going to cancel this out. And we're going to put pi radians up here. So now you're like, okay, how do we plug this all together? Your calculator normally has the symbol pi, but if it doesn't, you can just plug in 3.14. So you would get 37 times pi, and then we have radians left over, and we cannot forget the 180. So if you plug that into your calculator, it's 37. On Google Calculator, if you just put this pi, that is equal to pi. So if you just type in pi, Google knows that's pi. So I'm going to put 37 times pi. Oh, I was plugging it on here. Times pi divided by 180. That's going to give me this value. So this is equal to 0.6 6 radians. It's not as easy to conceptualize this, right? But we know that 37 degrees is equal to that in radians. So there. Utilize this information to understand how to convert from degrees to radians. And so now I use this segue to get us here, but we still haven't finished talking about angular situations. We've already related angular velocity to linear velocity over the radius. And so you best believe that this applies to both position and acceleration too. There's angular position or angular acceleration too. The counterpart to position is called theta. This is an angle because you're actually getting an angle as you travel in a circle. Excuse me, I'm nasty. The burping right here. So the way you connect the two is the same format as for angular velocity. Theta is equal to x divided by the radius. And now acceleration, its rotational counterpart is called alpha. It's another Greek letter, alpha. And I'm sure by now you guys kind of see the pattern. It's linear acceleration divided by the radius. Radius. And just to complete the picture, omega, like that. It's like a W, but. So here are these 3 equations that you guys want to just have in the back of your minds. It's going to be really important when you're trying to compare linear to rotational. If you're asked to find the angular velocity or the angular position or angular acceleration, by knowing how to compare it to the linear counterpart, and if you know the radius, you're good. And so just remember the units. We already talked about angular velocity, it's radians per second. For theta, it's just radians. And for alpha, it's radians per second squared. So you can see the relation. Instead of like meters, it's radians. Meters per second, it's radians per second. Meters is just radians. Meters per second squared is radians per second squared. So this is the relation. Hopefully this makes some sense. Just keep that in the back of your mind. Okay. Was there anything else I think I've already gone over like a lot. I'm looking through your guys' questions to see if there is another situation. But yeah, you guys will have some questions on this. This should be plenty to get you guys started. I overkilled it. I went over a lot, but I hope this helps. If it doesn't, my apologies. Reach out to me if you guys have questions. Use these equations. They're going to be really useful. The first set of questions in the practice quiz will be related to all of this stuff. So I hope this helped. To recap, we talked about rotation and how going in a circular pattern, you get an acceleration that we call centripetal acceleration. The way to define a centripetal acceleration is the velocity squared over the radius. And then we talked about the relation between radius and diameter. Then we brought up an example, how you apply it. Then we talked about the universal, the universal gravitational force equation. I can never remember the actual name. Big G times big M times little m divided by radius squared. I haven't mentioned this, so I'm gonna give you guys a value for G. You can type in Google gravitational constant, and they will give you the number. G is equal to 6.673. I'm just giving you more digits than what you need, times 10 to the negative 11. And the units are newtons times meters squared divided by kilograms squared. So it's funky units, but that's just because it needs to cancel with everything else in there to end up with newtons. But yes, this is what the G constant is. For any problem you do, this is the value that you use for G. Keep that in mind. So then after we talked about this, I gave you guys an example of how you can connect the two centripetal force and the universal gravitational force into getting information. In this case, the velocity to go in a perfect circular orbit. And then after that, we went on to rotational counterparts to the linear acceleration, velocity, and position, which are angular velocity, theta, and alpha. And here's the relation. And then lastly, we talked about this new unit that comes from this called radians. And in order to convert from degrees to radians, you follow the same things we've done with other conversions, but instead you have to understand a relation between angle and radians. The easiest one is knowing 180 degrees is equal to pi radians. And then you can use that relation to convert. You can go from converting from radians to degrees or from degrees to radians. So keep that in mind. And that's it for today's topic. Please comment below if you guys have any questions. This video, I don't know if I mentioned this, but it's unlisted, so nobody can see it besides you guys with the link. So if you guys put any comments, I'm only going to see it, or your classmates too. It might benefit them. But if not, you can email me, ask me for questions if you guys have any. But with that being said, I'm about close to the hour. I'm sorry it took this long. I didn't mean to, but thank you guys for listening in. And again, thank you so much for your amazing effort. Honestly, like I'm so grateful for everything you guys do. We're going at a faster pace than normal, and you guys are sacrificing a lot of your summer for this. And then with the whole COVID pandemic situation, it's a lot. So do reach out if like legit you guys have any like unwarranted circumstances. Like just communicate with me, you guys, because that's the best way for us to move forward and all excel. And last thing, I'm going to get all your exams graded by the end of this week. They're going to be up latest by like Tuesday. Don't worry about the raw score. That doesn't mean anything. I have to go through it and grade it. So whatever score you saw doesn't mean anything at all. It's going to be completely different once I actually evaluate everything and grade it properly. And of course, if I see that everyone ended up doing a lot less than the average, I'm going to curve it, push it up. And I do that because it just shows, especially in these circumstances with online, COVID, all of that, that there's other factors at play that makes learning a lot harder. And then also communicating online, another deterrent. And so I have to adjust things properly. Of course, also my lecturing and the lack of it, if I can say so. And so I have to, I think it's only my civic duty to adjust grades accordingly to how the average of the class is doing. Because I believe if we have like around a B average, that means the test was pretty fair. And so if that average ends up being a little bit lower, I'm going to push it to, it's kind of like a check and balance to make sure that the exam overall represents the true capacity within the circumstances we're all dealing with. So that's a little bit of that. I will give you guys more details on Tuesday once I have everything graded and explain more on that. But yes, thank you guys so much. I'll catch you guys. I'm going to see you guys on Thursday. But if you don't see this till after, I'll catch you guys on Tuesday. Bye, everyone. Let's go. Let's go. Have a good one. I'll see you guys soon.